Okay, so here we've got a set of parallel plates that are 0.82 millimeters apart with 32,000 volts across them. And we're going to sort of connect to what we were talking about in the last video. This quantity right here, the voltage, this is what's called electric potential. So our electric potential, or V, is 32,000 volts. And that's basically it. There's not much else you can do with this except find the electric field. We can't find potential energy, we can't find work, we can't find anything because there's nothing between the plates. It's purely potential. Okay, so that's what voltage is. It's purely the potential for something to happen, and that is it. My favorite analogy for this is a slide, actually. Okay, so here's a slide. So what's a slide good for? Well, absolutely nothing. Okay, a slide sitting there by itself does absolutely nothing. It's not good for anything. But there's potential for something to happen. If all of a sudden a little kid shows up, there's a little kid, okay, little kid, we'll call him Trent. Here's our little kid, Trent shows up, and if Trent wants to, Trent can use the slide. Trent can, walk up the slide and then slide down the slide. Then he's actually using the sled. But until Trent shows up, the slide is totally useless. The slide has potential for something to happen, but nothing's going to happen. It's not until Trent shows up and uses that slide's potential in order for it to give him potential energy, which then he can use and turn into kinetic energy when he slides down. So the same thing applies to parallel plates. Electric potential is useless until you actually put something between the plates to let that electric potential turn into potential energy so they can actually do something with it. Okay? So there's not much we can do with it right now except we can find the electric field. So if we found the electric field, the expression we had for electric potential last time was V is equal to E times D. So to calculate the electric field, that is just the electric potential or voltage divided by the separation between the plates. So we can just take those two values, we can take that 32,000, and then we can divide that by the separation between the plates, and keep in mind that it is in millimeters. So be a little careful with that. And if we do that, we get about 3.9 times 10 to the 7 newtons per coulomb. So there's electric field. Now, that's all we can really do with that. Until we actually put something there, that electric potential is absolutely useless. So let's put a charge in there. Let's take a proton or another charge, doesn't matter. Well, let's take whatever charge you want. Let's put a charge in there. Okay, so now that I've put a charge in there, the electric potential now supplies potential energy to that charge. So let's see if we can find out what is the potential energy of the charge. Now we need a couple things about the charge. Let's make up a couple different values and that type of stuff here. Let's say it's a 7.5 nanocoulomb charge, and let's say it's 4.2 times 10 to the negative 10 kilograms. Let's just make up something. There we go. Okay. So let's find the potential energy of the charge. Well, potential energy is Q times V. The same way if you introduce a Q into the expression or the situation, you introduce a charge into the situation, it has potential energy. If you introduce a Q into the formula, it's got potential energy. So to find electric potential energy, that is Q times V. Oops, double Q. That's just Q times V. Okay, so Q times V. And some people just know it as, QED. That's the voltage right there. It doesn't matter which variation you use. It's all the same thing. Okay, so the same way we introduced a Q into the situation to get potential energy, we can introduce a Q into the formula to get potential energy. So to calculate electric potential energy, that's Q times V, or QED, and of course that is the exact same expression we had for work last time, because that's what it is. It's the energy, it's the work, it's all the same type of thing. Okay, so if we take this, we can now use this to calculate the potential energy, either using the Q times V if we wanted to, or the QED. It doesn't make any difference. We have the voltage, we have the Q. That might be the easier way to do it. So we've got the 7.5 to the power of -9 coulombs, and we multiply that by the voltage of 32 grand. Then we'll have our electric potential energy, which is around 2.4 times 10 to the -4 joules. Okay, so with this, now we have the potential energy of the charge. Okay, so this is the work that was done. We're just talking about that. So what you could do with this if you wanted to, you could do force is equal to work divided by distance. You could calculate the force going across the plates if you wanted to. You could then connect that to MA if you want to find the acceleration. You can do lots of things. So this was the potential energy of the charge. That would be the work required to take it all the way across. And of course, the other thing that happens is this electric potential energy, of course, changes into kinetic energy. So that 2.4 to the -4, that was the potential energy. That is also the work done. That's also the kinetic energy. It's all the same type of stuff you guys done before. So we can use that 2.4 times 10 to the -4 joules and make that equal to 1/2 mv squared. And we could find out how fast it's going when it hits the opposite plate. So if we just use our basic 1/2 mv squared formula, we've got the 2.4 to the -4. We can just take that energy times by 2 and then divide it by the mass that we made up, which is the 4.2 to the power of -10. And then don't forget to square root it. And we will have a speed of about, I'll round off a little bit here. Let's take around 1.1 times 10 to the 3 meters per second. So again, you could have found the speed by doing F equals ma, QE, kinemax, all the basic stuff, but you can also use the energy stuff as well in order to find out different things about it. Okay, so let's try another one similar to this and see what we can come up with. Okay, so let's try this one. Here we have an RA nucleus in between two plates with 800 volts attached to them. So first of all, a nucleus, I'm going to need the mass and charge, so I'm going to start with that. So I'm going to find my charge and the mass of my nucleus. So I've got to look up the atomic mass, atomic number in the periodic table, and then multiply them by the numbers. We've done this type of thing before to get the charge and the mass. So the charge you should get is about 1.41 times 10 to the -17 coulombs, and the mass will be about 3.77 times 10 to the -25 kilograms. Again, that's all that charge and mass stuff that we did a whole bunch of in grade 11. Okay, all right, so let's see what we can find with this. So we're going to find a few things actually, or a couple things. Let's see if we can find out how fast is it going when it hits, as well as let's see if we can find out maybe the separation, how far it's actually gone. There's a couple things that we could find, and we can see what we're going to do with this. And let's see if we'll find a couple of things. Well, we'll see how things go, but let's do one step at a time. Okay, so we're looking at the work and energy type stuff. We're talking about, there's potential energy, there's work, there's kinetic energy, and you can go back and forth between all these things. Generally for these two, the common expressions are Q times V or maybe Q, E, D, typically 1/2 mv squared for kinetic energy. But the thing is, all these energy expressions are equal to each other. It's all the same thing over and over again. You just, as long as it's going all the way across, one is equal to the other, it's no big deal. Okay, so let's start with the speed. We've got the energy and stuff laid out. Let's just see if we can find the speeds. So speed obviously would involve the kinetic energy, and all I have to do is take my kinetic energy and solve for the potential or the work done. It's all the same idea, and all these things are equal to each other. So a lot of this has to do with, just like when you guys did mechanical energy, like mgh and 1/2 mv squared, equating one kind of energy to another kind of energy. So the potential energy of the charge would be equal to Q times V, and that turns into kinetic energy. So those two have to be equal. So I can use that to solve for how fast it's going. So Q times V or in this case it's a capital Q, doesn't matter, 1/2 mv squared. And I can rearrange for my v value, and my v squared would be 2q times v divided by m, and apparently I'm using small q now. Something like this. So when you solve for your v, don't forget to square root the expression, but you got the 2, the charge is the charge of the nucleus, the voltage is the 800, there's a mass right there, and don't forget to square root, and you can get the v. So if we punch all that out, we should get a v around 2.4 times 10 to the 5 meters per second. Okay, so let's see if we can find something with the distance as well. Well, if we look at the expression though, we do have an expression with distance in it right there, but we don't have the electric field, and you need to know the electric field to find the distance. So let's come up with an electric field and then we can work from there. So let's say that the electric field is, let's say it's 8.6 times 10 to the 5 newtons per coulomb. All right, so there's the electric field I'm going to give you. All right, so once you have that, you can find the distance across, and you could do work equals FD using QE with the electric field. There's lots of things you can do. A lot of people, what they would do is they would just use that combination right there, where the electric field times distance is equal to V, or VED. A lot of people remember it that way. A lot of people just use that. So then, of course, the distance would be the V divided by the electric field. Well, you've got that distance. That was the, or not, you got the voltage, which is that 800. You've got the electric field right there. So you can just divide the two out. And I think you should get around 9.3 times 10 to the 4, or negative 4 meters. So that's just using the VD expression. So again, it's just another way to do these questions. Energies often works really, really nicely. There are certain things that we will be doing with energies more specifically later on, but you can still apply it to all the basic parallel plate stuff that you guys have done. Okay, and again, it's all about finding one energy. Find the potential energy is equal to QV is equal, or QED, whichever you prefer. Make that equal to 1 FMV squared. Make that equal to FD, whatever you want. Any combination, they're often just all typically equal to each other. Okay, and then you can solve for whatever you need to solve for. Okay, so again, basic scenarios from grade 11, just applying the grade 12 energy ideas to them.